Hello, everyone. Thank you for having today on the show at CppCon. I'm really happy to be there. It's my first time in the US. I hope my French accent won't disturb you that much. Don't hesitate to tell otherwise. We only have 30 minutes, so I will take the question at the end. In any case, if I will stay outside for further questions, if any. And yes, let's discuss what is WebAssembly and how can you put C++ everywhere with WebAssembly. So just a small question. Do everyone know what WebAssembly is? Yeah? Okay, so some people. I work in a company where we built a small tool to generate WebAssembly software based on another tool which is named Unscripten, and which allows you to write C++ application directly inside HTML5. We'll see that. And work through installing all the setup, all the compilers for all the platforms, all the generating the build files and so on. But this talk is not about it. I just use it inside this talk. This talk is about using C++ 17 techniques, or C++ techniques which are older, to come up and bind with the web. So a small WebAssembly primer for those who perhaps don't know what WebAssembly is. So WebAssembly is a binary instruction format. It's a stack-based VM. I put a VM in quotes because it's not, properly speaking, a VM in the end. We'll see that. And it enables C++ to run in the web browser at first, within a JavaScript engine. But it also allows you to run it on the server with the same ABI, with the same instruction set, and to have in this way a flexible deployment of your software. So it's since last year, or beginning, yeah, since end of last year, a standard, but browser-rich consensus. So it's implemented everywhere. It's available in Node.js as well as in Safari, Chrome, Edge, Firefox. You can use as well other techniques to run WebAssembly code in browser that doesn't support it, but the support is quite good, so just keep with this. It brings portable binary instructions. That means you can write a C++ program, compile it down to LLVM bitcode, for example, and then it will be translated to WebAssembly. And this WebAssembly format is a format that has been thought from the ground up based on the experience that the people did with ISM.js and Pinnacle at Google, at Mozilla. And they implemented a file format which is really sleek and thought to be directly loaded and transpiled while it's being streamed from the web, and directly transformed to the native instruction set that you have on your machine. And that's why I put VMs in quote, because actually, once the file has been streamed in your PC and it has been transformed in native instruction, the WebAssembly runtime isn't there anymore for you. You are running directly on your instruction set. The only moment where you need to come back to the WebAssembly runtime is to grow the memory or to access host bindings functions. But if your C++ code will run totally independent of being JITed or so, once it's compiled, it's compiled. And you can use the optimization techniques of compilers, like you do on a direct build for a native platform like x86. Because in the end, the bitcode that is generated, the WebAssembly is just another kind of platform like x86. So it's like a portable executable or ELF format, but for the web. It has many advantages because it's PE or ELF without all the legacy. It has been designed new, especially for the web. So they could just take what was useful, just take the important part and let away all what was legacy from other platforms. And if you don't mind, I can show you how a WebAssembly module structure looks like, what happens when you build it and what comes out from the compiler. So taken, you have the reply to the world. Well, okay, it's from the each equals grade from the galaxy. It's a bit wrong here, but I like 43, so I kept that one. When you compile it, what you easily end up is a file prefixed with a magic number right at the top under the ASM chars, and then the WebAssembly format, which is there. And at some point inside this format, you have the different function and the constant and so on that you have that you add in your program. Like if we can see here, we have a main quite at the end. So this is the main function symbol, and it doesn't do much. That's why it's not that big. And it has a name as a string, so that it can be dynamically loaded by the host environment. But not all function needs that. Then if you look at a module, in WebAssembly, you can actually, out of the binary format, you can generate a WAST file, which is a textual representation of the binary format. A lot of the tools that the people developed at mscripten and so on, Binarian, they use actually the text format to do some transformation and come back, or just for debugging. And it's quite handy to look into your generated assembly as well. So if we take the function that you had before, we will see the 43 number, which is the constant that I return. So because it's a stack-based VM, what happens, I just push the 43 number on the stack, so that the return operator will pull it out of the stack and send it back to the caller. What you have is a type for function types, actually. Like, there are only function types in WebAssembly modules. There are no other types. Everything is a function, so to say, because that's the only entry points that WebAssembly modules are interested in. And you can encode the different type that your module is exporting. And then also encode the types that you can import. So the main function and get total memory, they share the same type. That's why you don't need two types for the different functions. And in this case, we are saying to the host environment, we need the dynamic symbol or the JavaScript function, so to say, because WebAssembly is meant to be embedded in JavaScript at first time, but it's not limited to that. To, for example, read what is the available memory. And then we export, we declare our own function, as I explained, and we export it so that the host can find it and call it, knowing the type. So based on the type, he can then call it. And in the end of the file, and this is important to note, you have the data segment. You have the static data segment that you perhaps know from BSS or so from other file format. And it's at the end of the file because so when you download a WebAssembly file in a browser or by an application running it, it will already start compiling the instructions before the data arrives. And then when it's done compiling, generally the data were already downloaded and can directly be mapped to memory, and the program can start with the initial memory representation. So it's really efficient in this in the way it starts. On the runtime that builds WebAssembly generally caches the build file. Then, if it doesn't change, it won't rebuild it anymore. You see, actually, this process here. You get the code and the data. The code is at the top. It gets downloaded first, and as soon as the download began, the different browsers, namely Firefox with SpiderMonkey engine and with on V8 engine of Chrome, they download and directly translate through a direct representation of the instruction set of WebAssembly instructions, and then they start executing right ahead when they have everything that they need, like a static initializer and so on. And if they have time then on the machine that they run, they will re-optimize the compilation that was done and generate even a better JITed output. But what happens at first is a direct transliteration of what you compiled to the native instruction set of the machine. And if we take the 43 example that you were returning, on x86 it will simply output such an x86 assembly. And on ARM64, like a normal function, a main function as well, 43 will be moved and returned. So that is to show that WebAssembly is not a toy, is not another VM runtime, or it's really simple format that gets compiled natively. So the Wasm runtime. What is interesting is how do your application work then when it started? You need to access data, it needs to allocate memory. And this has been implemented in a different fashion in the past in previous implementation from WebAssembly draft or from ISM.js. But now, and what was standardized is that a gigantic contiguous memory segment is allocated to keep your heap and your stack inside it. That means that you don't have any garbage collection which is occurring. Because as the heap only in the memory segment, the stack is separate. Because you manage the memory as you would be used to in C++ on a native platform. It's not different anyhow. But that generates an issue. There is no garbage collection, and the point is that browsers, mainly browsers, or Node.js runtime, use garbage collection for the object that they put at disposal over the web API. Like, say, an HTML page is made of DOM elements. The DOM elements are like XML nodes, but it's not XML nodes. And these nodes are garbage collected when they are not no more used and so. And from WebAssembly, you cannot directly access these references. You cannot grab them. And this obliges you to go back to the JavaScript runtime, to ask him to take a reference for you and to handle the mapping between JavaScript and WebAssembly yourself to map to the object that you need from the browser. So this incurs a little overhead. And this makes some steps, and this will be in WASM 2 changed. There is an active proposal which is being implemented and so. Which directly brings the different types from the browser, the different GC references from the browser to WebAssembly so that we can directly call in and out to the host runtime without moving through another mechanism, which in turn is JavaScript. But for the moment, we need to go over JavaScript. If you're interested in the detail of how the JavaScript and WebAssembly or ISM.js back then works, you can look at the nice talk from Chad Austin in CppCon 2014. It's mbind and mscripten blending C++11 and JavaScript. This explains very well in detail how this works, and this is still what is used nowadays until we have this new proposal implemented. So, sorry for the screen resolution, there is a bit of stretching of the slides, but thank you very much for bearing with me. So pthreads, you can use it because it's often a question that is asked. You in a JavaScript runtime or in a web browser runtime, you have only one thread, and this thread is called on yield back CPU time to the browser each time it's done. But in WebAssembly, it's possible to use pthreads. It's possible, that means to make a threaded application inside the browser or inside Node.js. However, it is based on shared array buffer, which has a bad reputation since the terrible Spectre security flaw came in. That's why all browser vendors disabled automatically a shared array buffer. But you can still use it if you enable it, or if you take the latest Chrome, they have re-enabled it because they fixed the different Spectre issue that they could have in this regard. So in Chrome, it's working. For the other, it's disabled for the moment. So who knows when it will be enabled again. So inside the browser, might perhaps not use pthread. In Node.js, in any case. So now that we know what WebAssembly is and what it can do, I would like to show you what we can do with C++ and WebAssembly, because it's good to have a runtime, but it's better to use it. So there has been, in the past, a rise of JavaScript in the web, which is a really nice language, dynamically typed, which has, I think, some things to share with C++ in the philosophy. But it's really different from C++, from the way of working. It may seem more flexible sometimes. And we can question, are these two irreconcilable worlds that we cannot work together on a JavaScript application, on web application with C++ directly in the browser? I think a lot of people have proven not. But it's not like there has been a mass adoption of this technology. So I think I wanted to say this. Neither Bjarne or Brendan wanted the language to be limited to what they could imagine. And I think this is represented in C++ with the template metaprogramming. And by JavaScript, it's the object.prototype, which is kind of runtime template, I would say, because you can take an array and change the subscript operator for everyone, just like so. And this allows JavaScript to evolve and to evolve by the user, and it's like C++ in this regard. So, but then there's been TypeScript. And TypeScript is, for me, it sounds pretty strange at first, because the key selling point is JavaScript that scales. It happens that the people developed a web application in JavaScript, and they seem to have missed some of the structure that a language like C++ is giving. So they have made a TypeScript. And the goal is enabling practices like static checking and code refactoring. And for me, it sounds like, why? But C++, it's all about this. It's all about static type. It's all about having the error at the compilation time. It's all about knowing before you ship that your software will run, even if an untested software doesn't work. But yeah, that is a Bjarne quote. So could we use it as well as TypeScript to make web apps that scales? This is a question that I ask. And if you look at the TypeScript website, actually it has the Seattle skyline, which is pretty nice because here we are in Bellevue. And I asked myself if instead of TypeScript, we couldn't have here written C++, because C++ could also be a way to write web apps that scales. And I say it is possible with what we've done at nxxm, with what the people like CppCon and Juge and so have done by mscripten. You can nowadays just open an HTML file, write script type text C++, and then use some library that maps to the browser API, for example, the DOM API, and say, OK, get element by ID. Grab the banner where is written TypeScript, grab a banner where is written C++ in it, and just make one visible and the other not, and fade them in and out. So this is a framework which is named Bellevue as a gift to the conference. And we are building it to make web development better. And I hope you will enjoy it and you will join us to improve it furthermore. We are open to anything. We have a lot of ID, not enough resources for the moment. And so could you make some room for C++ in this case? So if I take this code, I have to compile it too, because it's C++, it's not directly interpreted by JavaScript browser. So let's do that. I'm going into the example. And let's open the index file. So it's a big index file from the TypeScript web page. It happens to have somewhere the logo. So here, as you see, we have JavaScript that scales, and we have a div which is bringing the Seattle skyline and so. And out of Bellevue, could we enhance that? So if I already prepared the file because we only have 30 minutes, otherwise I would love to type in front of you. It's a good exercise. So what I did is I added in the file, I added a CPP banner. So here we had the JavaScript, the Typescript banner, and here we added another Skyline banner, which is for the moment displayed to none. And then the code that I presented you before is added there. The lambda needs to be mutable because we are modifying the captured copies of the element. The copies are actually holding a reference to the DOM, the banner TS and banner CPP. And so let's build this. So usually what will happen in the C++ world is, okay, download the compiler, install libraries, do all these things. With our tools, it's a bit easier. We have a file which is named nxxm deps. You had your dependencies as you will do in npm for the C++, for the JavaScript developers. You can specify a version, but you can also say just take the latest, I don't care. And then you can also specify security variable like hashes, checksum, and so. And then you can just say, okay, I just want to compile this and run it. So do nxxm dot, it downloads the library, infers the build that it should do based on the file that you have in your tree, and compiles everything. So here we have compiled it. So let's go back to the presentation. So if I click on this link, it will replace the iframe that is here. It will replace its source with the file that I just compiled. And this file, as we saw, has a main function, which is executed at the moment where the script is loaded in the page, and presents you with making some room for C++. And here we have web apps in C++ in the Seattle skyline a bit differently. So yeah, why not embrace this way of doing web apps as well? So thanks. Thank you very much. So, but then once you've done that, you have the browser side. But it doesn't make a lot of sense if you don't share it with your server side. So web services with WebAssembly, how can you do that? What would it bring you? So one of the things that we usually do as web developers is to write REST services. And it's a representational state transfer. I don't know, everybody is aware of REST and so? Oh, okay. So it's a way to write routes, URLs, and to make create, retrieve, update, delete actions on it. And in JavaScript, typically the people use on Node.js framework, which is named Express.js. And so they can write for a web server running at port 80, so the default HTTP port, the URL user as a parameter ID and so on. We in C++, we have such kind of stuff, but not for WebAssembly right now. And that's why in Bellevue, we also thought we can do something. And we can perhaps do something which is more type safe. Like here, who cares about the ID type? In this example, if you don't make extra checking, ID can be whatever and can lead to security problem. It's a broader attack surface the web developer are used to, but it's boring to always have to write if it's an int, if it's a string. So why not just write some template metaprogramming to parse REST APIs? So just to show you the input, first is you will give the URL that you want. You give the session, that's the server, it's bringing this to you. And then you give a name, min, max, and error range. And this allows you to parse automatically the different parameters. Like if it's a size t, then it will be passed as a number, but a string won't be accepted. And then we use other solutions to push this back in the data model, which is observable, and that will come to it. And this example is pretty easy. With C++ 17 or even a bit before, with the Boost library, so you can easily access to the compile time traits of a function. So you can remove the session arguments, which are not interested in the parsing of the URL. And then out of the splitted args, standard library doesn't have the string split, but yeah, we have sregex token iterator. So you can split the different part with the slash, and then for each argument, which are compile time, is a compile time list, a tuple of the argument of the function. Then you try to parse it with a library like QE, or you could use as well Boost lexical cast and so on. But in this case, we use QE, and it works pretty fine. It's one line. And then you just iterate further. And if it failed, you just don't apply the functor. This is a new C++17 function. Otherwise, you apply it, and you bring back a session. Typically, the session, you will put handles to the connection and so. And you can then make a tuple cat and merge it with the args that were parsed. And here you have type safety and security without any changes. So what this brings actually is also interesting is that we have this this universal reference syntax, that we can move the session object inside the handler. Because if you use write properly, the session can handle the connection, like a request close or request open. And if you keep the connection, then you can use it to send HTML server sent event and so on. We have implemented that as well. It's available in Bellevue library. So, but let's test it. So if I go to these services and I say hello as the first string, it must be well encoded if that's special character and make some numbers, then it will be parsed. So I will just write something useful, hello, it's better, and the different arguments are parsed. So, but what am I doing here? I'm adding to something which is named benchmarks. Yeah, because I think what you are interested in is looking at how fast is the WebAssembly in the browser. So let's go to this. We don't have so much time, so I will skip this part. Okay. So here we have a runtime benchmark, because I don't like benchmark which are, how can I scroll that? Like make it smaller. Okay. So I don't like benchmarks that we do on your end, and then we say it's fast and believe me and trust me. So I just wanted to make it in front of you. So this is running a function which is inserting in the playground below text, which is then requesting the browser to render. And so you can test the C++ performance. You can click, it's doing like 1,000 times insertion, and the times are in microseconds. So at the maximum time, we had 1,800 microseconds to insert 1,000 times a text and ask the browser to render. And there we see the limitation of this binding is that JavaScript is often 2 times faster for the moment in comparison to C++ in calling back the browser. But it has some drawback as well, because if you run it a lot of time, at some point, yeah, oh, you saw it. At some point, the browser is obliged to make garbage collection of the object, what we don't need to, because we have heap and we have reference counting if we use a heap allocated object. And then we are 2 times better than the JavaScript. We are more stable than the JavaScript execution when going back to the browser, so we have more guarantee. But it's slower in this case. And then you can save your benchmark result here. And what I made here is that the REST API that we used before is actually pushing into this. So if I take this example again, and I make another window so that we see it. Then if I write it here, actually with compile time metaprogramming, with the Boost.Fusion ad abstract or Boost ANA, and we've added some technique from C++17, like a proxy object and so on. we detect the changes to the vector, to the data model, and we directly push them back to the WebSocket to your end user. And this is also open source, it's work in progress. And so if I add things, it just get pushed to the browser directly. And no, this was not parsed because I made a mistake. So yeah, let me just show you if I can write something else. So this is interesting because you can, with WebAssembly, actually, even if you are a bit slower to accessing the browser, you can be faster in the end, because you could just abuse the fact that WebAssembly shares the same, you compile the WebAssembly module with the same compiler, the same flag, and nxxm does that for you, and that you have a consistent runtime across all platforms, and that you can just do simply std copy of your byte if your type is trivially copyable. And with step 17 and if const expert, it's really easy to write. Actually, this function can be used to deserialize absolutely any structures and vector of structures or vector of structures and so on. So if you're interested, we can discuss of this after. So I think that this is a way using fancy pointers and so to remove the need to serialize big JSON and big bulk of things to have a better web user experience. And this is what we're building at nxxm. And we are now released for Windows, macOS, and Linux. So you can grab the tool, it's free. It allows you to compile HTML and C++ inside HTML. We will ship cloud services in the coming month. And so that it gets also done online. And we are working to injecting lambdas and perhaps making it a standard for HTML5 as well in the end. So thank you very much. I think I'm over time.